Hello, everyone. I hope we have no more problems because we had a problem with streaming, so it took a little bit longer than usual to set it up. Before moving on to the talk, I think I would like to say a few words about the scope of the colloquium. So the scope of our colloquium is not only to discuss specific topics of electrochemistry. The aim is also to demonstrate the immense and inner complexity of even the simplest constituents of the electrochemical experiments and processes. So I hope in these colloquiums we can raise somewhat better awareness of the enormous complexity of the physicochemical phenomena that may look at first sight quite simple to many beginners in electrochemistry. And so today we will be discussing water. We use water in so many experiments, and both electrochemical and chemical, of course. However, water is one of the most unusual liquids that exhibit more than 70 anomalies in its physical properties and in the behavior. And so understanding what water really is at the molecular scale is extremely important for a wide range of electrochemical processes, from electrocatalysis and intercalation to things like corrosion and bioelectrochemistry and protein salvation. So today we're hosting Professor Anders Nilsson, who's among the leading experts in the science of water, aqueous solutions, ultrafast spectroscopy, and X-ray sciences. So Professor Nilsson, he received his PhD in Uppsala University in 1989 and stayed there as a physics professor until 2000. So after that, he had been a professor of photon sciences at Stanford University until 2015, and then moved back to Stockholm University, not back actually to just a different university in Sweden as a professor of chemical physics. So Anders, now the stage is yours.
Thank you very much, Andrew, for your kind introduction, and I hope you all can hear me well. So I will give this lecture today and talk about water and new revelations, so to speak. And as Andrew very nicely introduced this topic, that many people think take things for granted, and often we call it's just the blue background. But the blue background is actually quite interesting. It's actually quite complicated, more than you think. Often it's complicated when you don't understand it, but I'm getting back more towards that it's simple, and I hope I will at least give you a flavor that it might be simple if we really can understand it on a deeper level, what this blue background actually is made of. At the same time, this new understanding that we are developing about water, we don't know the implication will be in many different fields of science. And I think this might only be the beginning, so to speak. Let's see, now it doesn't seem to be working. Has it hanged? Something is unfortunately not working for me. Let's see if yes, I have to do it in that way. Okay. So here's a little bit outline for today. And I understand that in these type of seminars, you often have a break and it's a little bit longer. So I will first introduce some of the strange properties of water in a rather simple way, and then a little bit more complicated in thermodynamic response functions, and then talk about different hypotheses that has been proposed to explain this strange behavior of water. And after that, we can have some questions and a little break. And then I will come back to the experimental approach, to just briefly talk about X-ray lasers, and then mostly about the results, where we're going and test these different hypotheses and look at which actually work. This is usually how we do things properly in science. We can never prove anything. We can only test hypotheses and usually falsify. And there is usually one that we say is consistent. And based on that consistent hypothesis, we can explain, give an explanation for the anomalous behavior as far as we understand it today. And then I have just a little bit of an outlook for solid-liquid interfaces, how this can be important, which we still don't know, I have to say, but just a little bit of an outlook on that at the end of the talk. So let me start here with this slide, which is one of my favorite. It shows planet Earth. 2/3 of the surface is covered by water, which immediately tells us how important water is. On the left, what you see here is a biological cell. And also a biological cell is typically contains 2/3 water, which is often considered this blue background, so to speak. And this two picture just tells us immediately how important water is for our own existence on this planet. You will also learn soon that if water wouldn't be so strange, we would not either exist. Of course, I just threw in this slide, water and electrocatalysis, electrochemistry is taking place in water, and that of course should bring your attention to what you often consider the blue background, so to speak. Let me first just put a little bit of a scary picture here because it shows the amount of water we have on this planet. Here what you see is a dry earth where you took away all the water and made it into a sphere, as you can see there, the size of that sphere. Most of that sphere is actually ocean water, salty water. So now you see a little sphere there, which is actually all the fresh water on the planet. But most of the fresh water is still bound in glaciers and ice. So that little sphere that you are left now is actually all the usable fresh water we have, which are in rivers and lakes and in some of the groundwater that we can bring up. And we have to enlarge this one in order to see it. And it's only 60 kilometers in diameter. So that's a little bit of a shocking evidence of, we have to think about the water we have on this planet. So that is an interesting message. The other thing is, of course, that water is so unique in its properties, and I'm going to take you a little bit through this. I just found this picture to be very beautiful. So let's take a little bit of a quick look here of comparing a simple liquid with water. So here you will see where we have generated some ice ethanol, and we put it in the glass of liquid ethanol, and you see it sinks to the bottom. Now, if we instead take what you probably will already know, if we instead put now a glass of water and we put some ice in it, and of course what you will see is that the ice actually floats. So it's not ethanol that is strange. Almost all liquid behaves more like ethanol. Is actually the water that is strange. And if you look with the thermometer, you will see at the bottom of the glass is 4 degrees. And it's more 0 degree on the surface where the ice is, the surface of the water. So water gets most heaviest when it's actually at 4 degrees. And I'm sure many of you all know this, but many of you don't know what is the origin of that particular property. So here's two unique. Water is denser than ice, which means that the liquid is more dense than the solid. So that's very strange. And that we have a density maximum. On here on the right, you see density as a function of temperature, and in a normal liquid, the density will just increase as we cool it down, and water behaves like a normal liquid when it's hot, and then it starts to deviate. When it actually starts to come in around room temperature, it deviates from this linearity, and then we have a maximum, and then beyond the density maximum, actually water expands, and you will learn more that we can supercool water, and the expansion just accelerate as we go to cold temperature. If you think about these two properties, and if water instead would have been like all other liquids, which means that we would have on the bottom of the ocean 0 degrees, and also ice will always sink to the bottom. So during ice time and when we have winter climates, what will happen if that would be the case? So here you see a beautiful coral reef where we have fishes and everything on the bottom. And if we instead would have water as a normal liquid, the bottom of the ocean will be just endless ice and would have prevented actually marine life from developing on our planet. And of course, as we know, all the mammals came from the ocean, and most likely humanity or we wouldn't exist without these two unique properties of water. Another one, of course, that is very important for us in Europe, and particularly in the north where I am, is that water has a very high heat capacity, which means that it can store a lot of heat in it. So it's the amount of heat you need to put in to raise the temperature. And of course, this stabilizes a lot of the temperatures in the ocean because there will not be so much temperature variation as the water is flowing around in the ocean, since it takes more lot of heat to be removed to lower the temperature, so to speak. And in particular, this is very important for the Gulf Stream, that we can actually, thanks to the high heat capacity, get warm water up into Northern Europe, maybe not less important for Switzerland as it is for Sweden, but it actually stabilizes a lot of different climates on the planet. A simple liquid that we think about is usually surrounded by 12 nearest neighbors, and we have only one type of sort of atom. This would be like a monatomic liquid, but it could also be a simple like ammonia, or oil, or anything that will look a little bit like this. So water, of course, is not simple, and it's thanks to the ability to form hydrogen bonds. Sorry, I was too fast there. To form hydrogen bonds, and I'm sure that many of you, of course, know about that. But what is unique with the hydrogen bond that is that water can only form maximum 4 hydrogen bonds around each water molecule. And as I said, a simple liquid can have 12 nearest neighbors. So this actually can generate a lot of open structures, and you can also generate a lot of different types of structure that you will see soon here. So maybe here I introduce let's say, the more simple picture of the strange behavior of water. Here's more the physics of water. And what you see here are 3 thermodynamic properties. And these are in statistical mechanics called thermodynamic response functions. And to the left here, you see what's called isothermal compressibility. It's the ability for water to be compressed. But in the statistical mechanics, it actually gives you, it's sort of related to density fluctuation, actually volume fluctuation, but of course at constant pressure it becomes density fluctuations. And as what you see is that typically the normal liquid, the compressibility lowers as you lower the temperature like this. And water behaves like a typical liquid when it's warm, just what I told you about the density. And it goes down with decreasing temperature, and then it reaches a minimum here at 46 degrees. And then it starts actually to deviate, it goes in the opposite direction, and it gets more and more easily to be compressed. And as you can see, it really becomes accelerated, this deviation, as you get cooler and cooler below the melting point. So that's density fluctuation, and I will come back to that later in the talk because we're going to do measurements on this and see what's happening here when we go beyond the temperature that we see there. You have heat capacity, as I introduced, very important for creating all the climate zone on the planet. And as you see here, a typical liquid, the heat capacity lowers as we lower the temperature like this. And you see water has a little bit, is above a typical liquid, but that's why it has a high heat capacity, so to speak. And it follows again when water is warm, and then go through minimum, and this time at 35 degrees, and then it deviates, go in the opposite direction, and the heat capacity goes up as you lower the temperature, and it gets more and more accelerated. And heat capacity is related to entropy fluctuation in statistical mechanics. Then we have the third, which is the thermal expansion, which is of course related to the derivative of the density. And we see here again a typical liquid where you have a positive thermal expansion. So it means, of course, as we lower the temperature, the liquid will contract. Or actually, if you increase the temperature, it will expand. And water behave like that until it passes the density maximum at 4 degrees, and then it changes sign, and then you have a negative thermal expansion coefficient. And that property is a cross product between actually entropy fluctuation and volume fluctuation, which means then as it goes into negative, as the volume increases, so that then the density, the entropy has to decrease, so to speak. What caused a lot of interest about water is goes back into the 1970s, when Austin Angel, Speed and Angel, started to actually fit these deviations here. And they fit it with the power law. And they saw then that these seems to be deviating like a power law, or diverge, as is often called, towards a mystical temperature of 228 Kelvin. So something dramatic is assumed to happen down there around that temperature. They had only measurements typically around down to 240 Kelvin. So this was only an extrapolation, then that these properties will reach almost infinity at these very low temperatures. So something is very weird with water. Of course, down at the supercooled conditions, the weirdness is extreme, but as you can see, it's already start in what we call ambient temperature. And particularly noticeable is that this increase, this minimum incompressibility is at 46 degrees, and I might come back to that later on, that it's actually, that is around that temperature is the starting point when water starts to become anomalous, the first indication, which means that the water that we use in our life, that exists in our bodies, and of course that we use all the time, is already anomalous liquid. But to find the origin of this, we might want to go where it's really extreme, down into these supercooled conditions. And this has been a debate going on for a long time, what is happening there. One of the proposals that you will see me talk about, hypotheses, was developed with theoretical simulations that water could consist as two different distinct macroscopic liquids, so to speak, like this, blue and red. Sometimes I will actually, instead of red, use yellow, so I haven't updated all my figures instead. So you can see that we might, that is a hypothesis that water consists of two different liquids. It's almost like this. I have a picture on the right, which is just oil and water. So if you would think about that we could have water at normal condition as these two liquids, that you will learn that they will never be as two macroscopic liquid at our normal conditions, because then of course we would have discovered this thousands of years ago. But under very special conditions, and if we could imagine that we could have it in a glass, it will separate like in this case coconut oil and water. So it's macroscopic. And here on the left is a beautiful picture actually from Denmark, at the tip of Jylland, where we have Skagen, where the Baltic Sea meets the North Sea. And it looks like you have two different oceans, so to speak. The difference between them is actually there is quite a difference in salt concentration that makes them also to have a slightly different densities. So these two forms, if this hypothesis would be correct, might have something to do with the weirdness of water, so to speak. And the idea is that there could exist two different local arrangement of water molecules. Here's something that is coming out of a simulation where they actually could see that. And if you look on the left here, this type of arrangement has what we call tetrahedral water. It's not ice-like, because ice will make up six-layer ring, as you probably know. But this is a little bit more made up of almost five-member rings, but it makes a very open structure, so to speak. And we often call this low density because it has a lower density. And here instead, on the right, we have moved a lot of molecules to fill out that space that was opened up because of this ring structure, and you have a much higher density, and that's called high density water. And all of this came a little bit with this phase diagram that I will now explain. And what we see here on the y-axis is temperature, and in the x-axis is pressure. Yellow is stable water, which means that water is the lowest thermodynamic state, so to speak. And the dashed line here is the melting into ice. And here you can immediately see one thing strange here also with water, that the melting curve goes down as you increase the pressure, or for all other liquid it actually goes up. So the melting point will be higher as you increase the pressure. Of course, you pressurize it to make the solid easier to be formed at a higher temperature. In orange here is what we call supercooled water. And water can be supercooled, so can many liquids, actually. And that has to do with that ice formation as we know about it. Almost everything you see when ice is formed is because of heterogeneous ice nucleation. It means that it's a dust particle or an interface that forms a template for the ice to grow. And so if you have a very pure water, you can actually supercool it. But you can only supercool it typically down to this dotted line here, which has often been denoted the homogeneous ice nucleation temperature, which is not really a line at the thermodynamic line here. It's more a line of convenience for kinetics, which means that how fast ice forms on laboratory timescales when we can do measurements maybe on seconds or minutes. But you will see how we actually are going to beat this line with some new type of experiment. And the reason why it almost becomes a line is because the ice nucleation rate for homogeneous ice nucleation, which means that the nucleation to ice is not on the surface or a dust particle, it's spontaneous in the liquid due to a fluctuation in the liquid where you locally form what looks like a nuclei to start the ice formation. And the rate is extremely steep here. So just 1 Kelvin change will change the homogeneous ice nucleation rate by many orders of magnitude. So therefore it almost becomes a line here, so to speak. And that is what we call supercooled water. And you can see also that this line really drops down with increasing pressure. Then down here in the green area at low temperature, and I will speak a little bit more about what these are in after the break. There actually it was discovered that you can make what's called amorphous ices. Amorphous means then that is a solid that is no longer, it's not a crystal, it doesn't have long range order, amorphous. And it was discovered to a big surprise that there are 2 different amorphous ices. One called low density amorphous ice, which has a density not so far from hexagonal ice, and it's a disordered way of a little bit looking like hexagonal ice. So if you would put a crystal, for instance, in a vacuum chamber for surface science experiment, cool the crystal down to liquid nitrogen temperature and dose water onto your crystal, you will form this low density amorphous ice. Whereas if you heat it up a little bit, it will crystallize. But it's very easy to form this low density amorphous ice, and that is also the form that is very common out in space, on meteorite, asteroids, and so on, are usually this low density amorphous ice. Then actually it was discovered by Mishima in Japan that you actually could generate also something called high density amorphous ice. And that, as you can see, has a much higher density here. There actually exists even another form further up, but I'm not going to talk about that. And it was shown that it was actually a transition here between. This transition has also been quite controversial, with a number of papers question if it exists or not. And if you warm these amorphous ices up to higher temperature, you reach again this dotted line. And this dotted line is where ice will be formed very quickly, because everything below this dashed line, the thermodynamic most stable state, are always going to be crystalline ice. Not only hexagonal ice, but under pressure there exists a number of different crystalline ices. So the idea many people thought is that, and there are evidence, and we also have some experimental evidence that I will not talk about, that there might actually be the possibility that these amorphous ices start to move. You can start to have a diffusion as you heat it up, and that will indicate that you actually can go into liquid state here. And of course, in the beginning here, just crossing over to this dotted line, where crystallization might take place in the time frame of 10 or half an hour or hours, you can study that what we call ultra viscous is going to be like cold honey flowing extremely slowly. And there it's seen that you actually looks like you can have two different forms of this ultra viscous state. But the big idea is that further up, could there exist then two different liquid forms of these two amorphous states? And that's what's called the high density liquid and low density liquid. And as you probably should know from your physics or thermodynamics, that if you go from part of the phase diagram where you have two different phases into where you only have one phase, that crossing has to go over a critical point. And that is one of the proposals that actually there exists a critical point down in the water phase diagram. Water has a first critical point, which is between the liquid and the gas. So if you go up to 400 bars, roughly 300 degrees centigrade, you have a critical point between gas and liquid. And beyond that critical point, at high temperature and pressure, you can't distinguish the liquid from the gas. It's only one phase. The challenge is that all this interesting phenomena is existing in this gray region, which is called no man's land. And that is a little bit like the trenches in the First World War, that you can't go out of the trenches. So here's one trench and the other trench. If you will try to go in between, you will be shut down immediately. And here you will be crystallized immediately because ice will be forming so fast. So a lot of the research you will see now that I will present is our ability to use X-ray lasers to actually go into this no man's land. And in particular, as you can see, this temperature at 228 Kelvin is sitting inside this no man's land, which has prevented people for studying this. Let's see now. Does it hang when I? Yes. So, but you can generate supercooled water. I thought I'd show this, that if you can do it in your fridge, you can cool water down below the freezing, and you just a little bit shake it, and it will immediately crystallize. And this is only a few degrees supercooled water. But now we have to, when you are maybe around this region here, but it's only about time scales. And you want to have a small volume also, so you don't have too many molecules of water, but still being bulk enough to really see it. So if you look at this phase diagram now with pressure and temperature, and we have this indicated like a phase separation line between two different macroscopic liquids that you see would have a huge difference in density, actually. They will easily separate like oil and water. So that is indicated here now as yellow and as blue. And here you have pressure and temperature. And here is the coexistence line. And one hypothesis here is that you have a critical point that it ends in. And from that critical point into the one phase region, you only have one phase. And there, the system cannot decide if it wants to be high density and low density, and you get fluctuations, as you can see here, indicated by this blue region in yellow. So if you're higher temperature, you're more in the yellow, and you have just a little bit below coming in. And as you lower the temperature, you get more and more bigger blow and more of them. And then you have this dotted line here, which is what's called the Widom line. I will speak more about that later. That is when these fluctuations will reach a maximum, and then you will have exactly 50-50 blue and yellow, and then you will have more blue, etc. And this will be not stable structure, it will be fluctuating on some sort of time scales, the liquid. So this will then be the explanation for the anomalous behavior of water, because our condition is where it's fluctuating, but when we're on this side here or down here, it just behaves like a simple liquid, like all the other liquids, so to speak. But there are other hypotheses as well that people have proposed. And here are them. And you can put them a little bit on a similar phase diagram as this critical point hypothesis. So here again in the middle have the critical point hypothesis. One is that you move this critical point into what we call negative pressures. Actually, you can generate negative pressure, which happens sometimes in nature. Actually, many trees, through a biochemical process, actually make negative pressures to help the capillary forces to get water in up. And it's also often in different minerals, etc. You can have negative pressure. So that will mean then, as you cool water down, it will not go into fluctuation due to presence of this critical point. It will only go into fluctuation because it approaches a phase transition, because the phase transition line will be all the way here to atmospheric pressure. And this is called the critical point free model to explain why we would see fluctuation. Now, clearly, the fluctuation will be much smaller compared to have a critical point here in this case. The other scenario is what's called the singularity-free model. It's more like now we move that critical point all the way down to 0 Kelvin, and there is no phase transition. There doesn't exist two different liquid phases. And we instead have fluctuations everywhere here of this nature. And it often called percolation models also. But clearly, again, the fluctuation would be much, much smaller compared to that you would have a critical point in the neighborhood of what we call the ambient conditions. So these have been existed for quite some time to explain. All of them are related to that water cannot be homogeneous. Also some people that claim that around room temperature, that it's completely homogeneous, but I will not even bring that up because nobody can explain in such a model how you have a density maximum, minimum incompressibility, minimum heat capacity. It's just something people claim without actually having any solid discussion how it relates to thermodynamics. And some molecular dynamic model generates that, but they also are models that lack density maximum and lack the minimum incompressibility, etc. There was recently a fourth model that generated enormous controversy. They're actually proposed by a very famous David Chandler, or late David Chandler. He's not around with us any longer. But that came a debate within the last 10 years where he said there is never going to be a low density liquid. There is only going to be ice formation, and the only thing we see is fluctuations because ice is trying to be formed. When you do it, and so that has been a very, very controversial idea. So we have, so to speak, three hypotheses with critical points at different locations, and a fourth that everything is ice, so to speak. And I think I'd stop here for a little bit to see if there is any questions, and we can have a little bit of a break. Back to you, Andrew.
Thank you. Yes, I think now the audience can ask questions. So one question that is asked in the chat is if the liquid critical point lies in the no man land, how was the large increase and divergence, like the behavior of either thermal compressibility was observed?
Why would if it lies there? It is because the idea that the critical point lies in this no man's land and it's metastable, which means that it has a lifetime before ice crystallization long enough that it gives rise to liquid-like properties with fluctuations. If the ice would form too fast, of course it will never sort of create a free energy landscape to cause these fluctuations. But it's considered then to be a metastable state, and people can see that existence of that critical point in simulations. And there was just a paper in Science last year where they actually could clearly simulate this existence of this critical point and how different response functions would diverge due to the presence of it. So most of these studies so far of the no man's land region has been in theoretical molecular dynamic simulations, so to speak. But they all, of course, all depends on the quality of the description of these simulations. So, but you will see later on when we get into a little bit more details with the experiment, also how this fluctuation comes in.
Uh-huh. Any other questions? Anyone has any questions so far? Maybe I can just quickly ask also about the auto-ionization of water. As a chemist, I'm just curious, how does it really change with temperature when we go to super cold and especially into the region of lower temperatures? I don't know if it was really studied experimentally
You
or
mean
if any
ionization, how you can ionize?
auto-ionization, right? So the constant of dissociation, basically, if you look at it from a
Oh,
chemical point of view.
that is something I don't know. I doubt that anyone has looked at that. You mean the equilibrium to form OH and protons?
Right.
Um, so that will of course change the pH of water. If you would go down to the supercooled conditions, I don't actually know. It's an interesting question that actually could be important to get some information on. So, but I'm sure it will change. Do you
Okay.
know if it changed a lot if you heat water?
Yeah, I'm not sure exactly. I mean,
Yeah,
it doesn't change much, right?
yeah,
Uh,
yeah. It could of course change because all these processes will slow down. You know the let's say the rearrangement in the liquid form. You know you form and break the hydrogen bonds in all these different structures. Uh, when you cool the water down, that slows down, and um, and eventually you can cool it down all the way to this low density amorphous ice, which which is then also forms a glass. When you come from the liquid side, it forms a glass. So then you might go from room temperature down to that state, and you are changing 10 orders of magnitude of the dynamics. And I can only imagine that the auto-ionization will also change. But that's a good question. I have no answer.
okay. One more question from the chat. So I guess about the hypothesis, which one is more accurate, you will probably tell a bit later to us.
Yeah, we will test them with the experiment.
Right. But the one question that is related to the presence of ions, I'm not sure if it's the right time right now to ask it, maybe a bit too much in advance, but maybe you can also comment a little bit about like if you have some ions that have dissolved even a mild concentration of some salt.
Yeah. So what happens then?
Uh-huh.
Yeah, I can answer that. So that's an interesting aspect, of course, and I'm sure that from electrochemistry point of view, very important, and probably thinking about electrical double layer, etc. So if you as I said, as you will see also later on, we will have these fluctuations of HDL and LDL. At room temperature, water is mostly HDL, and you have these fluctuating small pockets opening up of LDL structures. If you put sodium chloride in water, it prevents the fluctuation into the LDL, and the liquid becomes slightly more homogeneous. Sometimes people have said it's almost like putting pressure on water, because you have the same effect by putting pressure on water. If I go back here, that if we put pressure on water, we are going a little bit more here to the right, so to speak, and we're getting into more pure yellow, so to speak. So if you put sodium chloride in water, we will remove this blue. But of course, to completely remove the blue, you need to have very high concentration, or almost saturated solution of sodium chloride. Other ions could actually have a little bit opposite effect. For instance, a fluorine ion might help to actually form more of the blue region. And of course, strongly charged ions will usually form a tetrahedral, let's say a solvation shell of water molecules that is very tightly bound, and that can also form more a template forming a little bit more of this blue. So it depends a little bit on the ion, but for the monovalent ions, you can actually kill some of these fluctuations, so to speak. But completely kill it, you need to go to a very high concentration.
Okay, maybe one last question before we continue. So are there any computational studies that predict the second critical point to be at negative pressures? One of the questions from the chat.
Yeah, there have been some computational studies that has indicated that, but maybe more from not let's say molecular dynamic simulations that have sort of proposed it. Usually, the molecular dynamic simulations, most of them predict the liquid to a liquid-liquid transition, and many of them will indicate that is plausible with a critical point. There is a few models that do not indicate it, but almost all models, as I might mention later on, predict where this critical point would be in the wrong place. So we don't have yet any accurate water models to be quantitative when it comes to the water properties. The computer models can still be, as I call it, computer experiments to see trends and get qualitative features, but we are not yet quantitative.
Okay, thank you. Probably we can continue then with the second part.
So how long break should we have?
No, I think this is it. We can continue from now. It's perfectly fine. Because later, all the questions then will be saved for the later.
All right, so let's now go and start to investigate this. So can we see such a liquid-liquid transition? And we will use X-ray scattering. That will be the technique that I will show in this entire talk. It's either going to be what we call wide angle, where the X-ray is scattered to a rather large angle, which is typically, some people call it X-ray diffraction, etc., where you can see, distances between atoms, etc. But we will also use small angle that is more scattering on longer length scales. And that, with that technique, particularly for a liquid where you don't, let's say, have colloids or pores, it's more that you generate a density inhomogeneity due to density fluctuations in the liquid that might be then on a certain length scale. And first we have to just show how do you prepare an amorphous ice, but in this case a high density amorphous ice. And here is a little bit of an illustration of that. What you actually do is that you take hexagonal ice and then you simply put pressure, so you have a crystalline hexagonal ice, and then you quench it. As you can see, everything is getting pressed together and you are generating then an amorphous solid. So the experiment we're going to do is that you're generating that, let's say, high density amorphous ice in a what we call a pressure machine. And you might go up to rather high pressures, and then you quench it down to 80 Kelvin. So as you quench it down, the amorphous ice is, you can take it out into atmospheric pressure, and the temperature is so low the molecule cannot move, so they are sort of quenched. And then you can heat it up, and then the system can decompress, as you can see here, because when you take it out, then you can say you have built in the pressure in the solid, which is not entirely true, because the solid is usually defined as the pressure on the outside. But if it would be in the liquid state, you would have sort of generated a high pressure state here, which is different from what you have in the surroundings, so to speak. And then by taking it out, you can then heat it up, and then it will decompress, so the pressure will be equal inside and outside. And as it decompresses, the system will then go into different pressure. We can call it a quasi-equilibrium in that state. So we're just going to look a little bit on the structure factor in X-ray scattering as we're going through this. So this is typically what you will measure in an X-ray scattering experiment. This would be more the low angle X-ray scattering. And here we have the different wiggles, so to speak. in the X-ray scattering is what we call the structure factor. And here you have Q space in reciprocal angstrom, so to speak. And we're going to focus on these two peaks here in the structure factor. So if we look at the two different amorphous ices, and we look at the structure factor, we see that the first peak here in the structure factor is different position for the low density and the high density, whereas the second peak here in the structure factor is actually almost at the same position. The reason why it's called second and first is more related to real space, because if you measure this X-ray scattering to a very large Q, you can do what we call a Fourier transform and then convert this into real space. And that will generate what we call then a pair correlation function. And that means that it's the probability when we go from one molecule or an oxygen atom in the center here, the probability to find other oxygen atom at different distances, so to speak. And that is called the pair correlation function. So here you can see then for the first peak will correspond to the nearest neighbor distance between water molecule, and the first peak is almost identical between low density and high density. And since in the structure factor is 2 pi over r, so to speak, it's reverse in distance. Therefore, the second peak here in the structure factor is actually more related to the first distance. Now, the second distance is distinctly different between low density amorphous ice and high density amorphous ice, as you can see here. And that is the reason for why this peak is shifted, the first peak, because we're going to use this signature now in many of the experiments to identify if we have high density or low density in this structure factor. We will do that in reciprocal space, but it's related to the second shell. And you can see why that is, because in low density amorphous ice, that is a little bit more similar locally with tetrahedral coordination as we have in ice. We have the nearest neighbor here between two water molecules in a tetrahedral configuration, which gives this first peak here. But the second peak comes then at the next nearest distance, and it of course corresponds to exactly this angle that you have in tetrahedral coordination, and that gives rise to this 4.5 angstrom that you have here in low density amorphous ice. In high density amorphous ice instead, we have quenched the structure a lot, and there are water molecules now coming in and filling out this space here in between. And they are coming out then in typical distances. It's a little bit disordered, but more distances of the order of 3.5 angstrom. And therefore you see here the peak at 3.5 angstrom in the pair correlation function. And that is what gives rise structurally to a shift here in the first peak in the structure factor, so to speak. So if you just take high density amorphous ice, again, we had a peak now, going back here, we have a peak of high density amorphous ice sitting around 2.15 reciprocal angstrom, so it's higher than the low density, which is around 1.7. So if we have high density amorphous ice, and we just heat it up to just go across that dotted line a little bit towards this no man's land region, but where ice formation still takes hours, we can actually see that as we decompress, that we go through a phase transition because the high density goes down, and you have almost here in between two coexistence of two features. And as you can see, the low density comes up. So we clearly have a first order phase transition here between the high density to low density as we decompress the high density amorphous ice that we have generated. So we can see that this is happening just around here, this dotted line in this ultra viscous state. But the question that is more interesting for us, is there also two liquid state here at higher temperatures, where water will be more low viscosity? Can we experimentally see that? And that, of course, opens up the challenge to how to do such an experiment. I just show you that you have a discontinuity between one state going into the other. Here is our example when water is not changing discontinuity like in a phase transition, but more a continual change. And again, here's the structure factor. This is more when we cool water down, and it's just changed continuously. Or if you have room temperature water, 290 Kelvin, 98 Kelvin, and you put pressure on water, this structure factor is just changing continuously. And that, of course, corresponds to that we are here in the phase diagram, we're going down here, we're going with pressure in this direction. So we only see a continuous change in the structure factor with either temperature or with pressure. So in order to do this experiment, we use X-ray lasers. I thought first I will talk a little bit about X-ray lasers, but I realized the talk will be way too long and maybe you're not so interested in it, or you can ask questions afterwards with X-ray lasers. But for water research, we actually have used all the X-ray lasers in the world, the one at Stanford, the one here in Korea, also in Japan, the European, and also I will show you at the end data also from the Swiss FEL, which is at PSI. We also been measuring water there. But for this particular experiment, we did this in Korea, and you can see a picture there of what's called the PAL X-ray laser. And the difference between an X-ray laser and synchrotron radiation that you also have at PSI, the Swiss light source, and the measurement that I showed you before of the high density and low density amorphous ice was done with the synchrotron. So at the synchrotron, you have, as many of you of course know, you have a pocket of electrons going around in a circular orbit, and it's passing either bending magnets or undulators, and then you have emission of light. But you get bunches like this coming out of X-rays. They are separated by nanoseconds, and the width of them is typically 50 to 100 picoseconds in most of the machines. And there is a rather low energy per bunch. In an X-ray laser instead, you have compressed this, and that's why you have a linear accelerator, because you can control the electron pulses, the bunches in the accelerator, electron bunches, to become extremely small. And with the help of that, you can generate the laser effect. And then you generated femtosecond X-ray pulses. Typically, we use 50 femtoseconds, but there are ability to just generate a few femtoseconds. And it comes one pulse, and they might be separated now by milliseconds. So most of the time, there comes nothing, and then there comes one pulse. Maybe every a few hundred per seconds, but the intensity by this pulse is enormous compared to the synchrotron. So it's almost like you're shooting on your sample instead. And for this particular experiment, we actually are doing exactly that. We are taking a shot because we control and only send in one pulse at a time to look what is happening, so to speak. And you have to be very careful not to destroy your sample because the intensity is so high. So what I will show you now is this experiment we did in Korea, where we have generated this high density amorphous ice that I just showed you how we can just heat up a little bit about the glass transition, where it goes into the liquid phase. But in this case, we are going to do the heating really fast. We are going to come in with an IR laser pulse. In this case, an energy 2 micron. This corresponds to excitation of a combined OX stretch and a water bend mode in the water molecules. And this pulse is only 50 femtosecond in width, so it's a really fast heating of the sample. And after we have then heated up the sample, we can then go to much higher temperature. We then come in with the X-ray pulse, and then we look what have happened, and we can come in with a different delay, so to speak. And the delay, since the sample is going to decompress because it's now quenched in the liquid nitrogen to 80 Kelvin, these amorphous ices sitting inside these holes. Actually, we generated these samples in Stockholm, and they were shipped to Korea in liquid nitrogen. And they were very specially a lot of development because this sample has to be very thin. And so it was quite a lot of, this is not a trivial experiment. So you can then come in with an X-ray pulse, and then you can measure on the detector here. And here you see one of these rings that you see from scattering of water. That corresponds to that first peak in the structural factor that I mentioned to you. So we can analyze with the X-ray what type of liquid state we have in the sample. So what we are doing is that we are generating the high density amorphous ice, we are heating it up rapidly up to this region in the supercooled water, but the viscosity is low and it will expand very quickly. Actually, with the speed of sound, it will be expanding the sample. And as it expands, it will go through all the different pressures. And we will look then with the X-ray laser what is happening as we move quickly into this no man's land. Can we capture the liquid there before it crystallizes? And can we capture this proposed liquid-liquid transition? This is just an example. Maybe I should just tell you quickly that we also took samples of hexagonal ice, and we showed that we can melt actually hexagonal ice with this infrared laser, and we can actually see the X-ray scattering of melted water. So we can really heat this very fast. So we are actually going to do this, generating this state here that will then be moving in pressure, and it will move almost at constant temperature because the cooling down of the sample is much slower, the heat conduction, than the expansion or the decompression, so to speak, time scales. So we can think about 4 different scenarios based on this hypothesis, what could happen in this experiment. And they have all been proposed, not exactly for this experiment, but relevant for what is proposed for water. One is that everything in this no man's land is only ice. There can never exist any liquid state at all because ice is formed so fast. You will only see ice. That's one hypothesis. The other hypothesis is that yes, you can go up to this up to the high density liquid from the high density amorphous ice up to the high density liquid, but you can never get into the low density liquid because it will immediately form ice. Then you have the other hypothesis that you indeed can go into the low density liquid and there is a phase transition, which would then also indicate that there is a critical point and we have all these fluctuations. Or there is no phase transition, there is only a continuous change, just like what you have here at high temperature, where we can change pressure and we only see continuous change in water. That is the fourth hypothesis. So now comes what will we see in this experiment. And here's a little bit of a cartoon. And some of this comes because there is a film that has been generated also about this topic, about water, and this experiment is in the film. So I took a little clip from that. And here is a little bit the experimental chamber, you can see. What you see here is, again, this sample compartment. An infrared laser comes in, heat the sample up, and then later on comes, of course, the X-ray pulses that we put on the sample, and then we get the scattering here onto the detector. Usually you think it will be symmetric, but this ring is offset because we put the center a little bit offset here in order to reach a little bit higher Q range in the experiment. And we put in only one infrared pulse, and then we look with X-ray, only one X-ray pulse, because the sample then has converted, so to speak, and we have to then repeat this with a new sample, with a new infrared pulse, and then a new X-ray pulse, and then we vary in the delay between the pulses. So we can think about what we might see. We put in the infrared pulse, the sample will expand. As it expands, we shoot it with X-ray pulses. And what could we see? Will we only see one ring appearing that is maybe changing in its position with time? Or we might see a lot of dots because we are forming a crystalline Bragg diffraction of ice sample. because ice crystallization is happening very fast. Like you can see here. Here's actually typical what you would see from ice. Or could we actually see a second ring developing? That would be the indication that we go into we have a phase transition into the other liquid state. So we do the experiment, then we come in with the infrared pulse, and then we come in later with the X-ray pulse with a certain delay. And this is just after 10 nanoseconds after the heating, and we only see one X-ray ring scattering pattern, which means that we only have gone into this high density liquid. We heated it up roughly around 200 Kelvin now, and we have a high density liquid. Now we are doing it at a later time. Now it's roughly 100 nanoseconds, and we start to get an additional intensity coming in. And after 3000 nanoseconds, we see a second ring developing. And here is the first evidence of two liquid states of water. And these are really macroscopic states of water, because you need to have an ensemble of water molecules to make such a well-defined diffraction pattern. So if I look instead in Q space, this is a little bit similar to what I showed you before, that we have the high density amorphous ice position as we heat it up into the high density liquid is the same. And then as we go to different delays here, we can see how this red start to grow. And this is the low density liquid that comes up. And then we can see that up to roughly 1 microsecond delay after we gone into that expansion. And eventually we see a little bit more, and now a little bit sharp features start to come, and that grows the sharp features as we go to 10 microsecond, 30, 100 after millisecond. And that is then crystallization happening. But we capture this liquid-liquid transition before the crystallization. And we can convert this now in different population, so to speak. Here is on a logarithmic scale, time after we started the expansion, after the heating pulse. So of course here in the beginning have everything as high density liquid, and then with time we see this conversion into low density liquid here. We don't convert the whole sample into low density liquid, because there will of course be many interfaces generated inside this sample, and we have a little bit inhomogeneity in the heating, but then we see the crystallization coming here, and that is eventually taking over, where it crystallizes into hexagonal ice. Actually, it's more a mixture of hexagonal and cubic ice. But the time scales between these are clearly decoupled, and we can confirm here by the liquid-liquid transition. And this was published just actually in November last year in Science. And we made a nice cartoon here that will illustrate that we can have two different macroscopic states of liquid water. As you can see in the bottom, the high density liquid, and on the top, the low density liquid. So, as we do in science, we can eliminate all these hypotheses. We didn't see instantaneous ice crystallization. We did not see that we first generated the high density liquid and then turn into ice. And we didn't see a continuous change, because that would mean that that ring that we had, or in the structure factor, the structure factor would have moved, but it stayed at a constant position, and it just turned into another peak, and that is this hypothesis. So we only have this one left, and the other three we can cross out. So the experimental data is consistent with the liquid-liquid transition. So it looks that there is such a line here. Now the question, what happens when we enter no man's land from coming above? Can we understand if there are these fluctuations? And if there would be a critical point, there would be then this what's called the Widom line. This Widom line would be like an extension of the phase separation line here, but into the one phase region. It will not be a phase transition line. It will be a line of maximum fluctuations. And that is well known for critical phenomena. So if you go to the first critical point between liquid and gas, you will see this line there where many of these thermodynamic response functions will diverge to that line. If you remember your physics, thermodynamic response function will diverge to the infinity when you approach a critical point like this. Maybe maybe I come that later. We do the experiment because we can generate small water droplets that we can inject into vacuum and cool it very fast. And when we did the first experiment on that, we had the cover in Nature. So it works a little bit like this. You generate roughly 10 to 20 micron size water droplets from a droplet dispenser. You inject them into vacuum and they undergo what's called evaporative cooling. By that, they very quickly lower its temperature, and you can vary which temperature you will have with the distance from the nozzle. And then you're putting one of these X-ray laser shots on the sample, and then you can look at the detector both with wide angle electroscattering and small angle electroscattering, and we can thereby probe because the cooling is very fast, and we can beat these kinetic limits of this high homogeneous ice nucleation rate, and we can actually go down to 227 Kelvin. Here you actually see a real photograph picture. Up here you have this dispenser nozzle, and here is this water droplet injected into that. And we can actually compute, and we also made some calibration on the way down. This is for the two isotope. I'm not going to talk about that specifically, but we can see how quickly the temperature lowers here. This is on millisecond timescales. And since the ice nucleation is a kinetic phenomena, we can then be faster. We can get to lower temperature before it freezes, so to speak. And we can also go into regime that ice is formed, because if you put one of these X-ray laser shot on a droplet, you might then see if it is a liquid, because then you have a water ring. In this case, the center of the scattering pattern is in the middle of the detector. Before I showed it when it was offset. So that means that the droplet is liquid, but if it has frozen, it will be Bragg reflections, and you will instead see dots. So we can go into regime where ice is also formed. We just only look at the droplet that never crystallized. The one that is ice, we just throw away the data, or maybe also analyze it for other purposes. But we only analyze the droplet that is still a liquid state. So the first question is, would we see now the liquid-liquid transition also here? We now saw that there is a liquid-liquid transition as we pass as we change the pressure. That liquid-liquid transition line can extend all the way to atmospheric pressure. So if we would follow then, let's say, the liquid-liquid transition, and we look at the position in Q space of this peak, either is high density liquid and then a new peak comes up as low density liquid, that would mean that we had just what I showed you before. Whereas if it will change continuously like this, it means that there is no longer a liquid-liquid transition, it's continuous. And we can then look at the derivative also for that continuous change and see where it's changing the maximum. And that could be a signal also for this, what's called the Widom line. And here is the experiment we did then with these droplets. Here we only focused on that first scattering peak in Q, and you can see how it actually shifts continuously with temperature. And here you can see the position as a shift, as we change the temperature going down. And this is now the derivative, ds1 dt, so to speak. And we see that there is a maximum in that derivative at this temperature of 229 Kelvin, which is very close to that temperature of 228 Kelvin I told you earlier on when Speed and Angel did this fit of the compressibility and heat capacity measurements, that it will diverge towards this 228 Kelvin. So something is happening there. But it's definitely not a liquid-liquid transition. So we can cross out this hypothesis that this liquid-liquid transition line will then go all the way to atmospheric pressure. We have seen it here, but now we can prove that it's not any longer here. So it means that we see a liquid-liquid transition here. We don't see one here. we go from a two-phase scenario to one-phase scenario, we need to have a critical point in between. For the physics as we know about solid and gases is correct. But we should still search, even if we can't get to the critical point, we can see maybe the smoke. If you think about the fire and the smoke, if you have smoke, there must be a fire somewhere. And the smoking in this case of the fire would be this Widom line. And that means that if I plot it here, if we come, then lower the temperature, and then we have these fluctuations, and this fluctuation that gives rise to this diverging response function, compressibility or heat capacity. And these will diverge to infinity if you go to the critical point. But the Widom line here will allow it not to diverge to infinity, but just reach a maximum. So if we can see such a maximum, it would mean that we have the smoke. And one way to detect that is to go look for density fluctuations, and I will come later to the heat capacity. So if you go for density fluctuations, and we can detect that by using small angle X-ray scattering. And I assume that most of you are a little bit familiar with that technique, since it's often used for looking at nanoparticles, pores, colloids, also biomolecules in solution. We are looking at things on the longer length scales, and you get scattering then between the edges, so to speak. But you can also have this scattering because you have density fluctuations, that the liquid no longer are homogeneous, they are fluctuating, so you have locally regions of higher and lower density. So if you look at water and you're approaching this very low momentum transfer, or Q here, a normal liquid will, this curve, I should have brought up ethanol here, but ethanol will only look like these structure factors coming down from the first peak that is more representing between atoms, so to speak, in the structure factor, and then it's coming down, and then it will sort of just approach almost perpendicular here towards Q equals 0. But if you have some inhomogeneity in the liquid, you will start to have a rise here at low Q, and this will go up. And that is because of density fluctuations then in the liquid. The shape of this will allow you also to analyze the size of these density fluctuations, but I will not talk about that. We also have done that. But what is interesting is that we can look at when this curve will approach Q equals 0 here. Because there is a thermodynamic relationship of the structure factor at Q equals 0 is related to the isothermal compressibility. This is Boltzmann constant, temperature, and this is the number density, or we can call it density, so to speak. So by this, we can actually determine then the isothermal compressibility, and it's one of the thermodynamic response functions that then should reach a maximum if the smoke, the Widom line, would exist. And we have tested earlier that this relationship works. So this is data points from this study where we have analyzed and determined the compressibility using this relationship at Q equals 0, which are these squares or circles. And the dashed line is thermodynamic measurement of the isothermal compressibility, so to speak. And here you again see the minimum here at 46 degrees that I talked about, and that the compressibility changes sign, it's change, it becomes suddenly rises at a low as you go to lower temperature, and that is of course why this goes up. So this experiment was very challenging because the VAX data, wide angle that I've been talking about before, sitting here at between Q 2.15 and 1.7 is quite intense. But the small angle is a very, very weak feature. And we needed to try this 4 times at the X-ray laser before we can really do these measurements. We need a very high quality detector, etc., etc. So It took a number of years development. But here you have the small angular X-ray scattering signals. Just looking at the more lower Qs, we are looking in this regime here, only here. As we lower the temperature, and you can see it goes up further and further and further and further. And the maximum value here is not at the lowest temperature, as you can see enlarged here. Actually, it goes up and then it turns back, so to speak. And if we integrate this intensity, you can see as a function of temperature that it goes up and then reaches a maximum and goes down. And if we use the thermodynamic relationship instead, we can see indeed that this isothermal compressibility goes up. Actually, it goes up tremendously. Maybe I will comment on that later on. And then it reaches a maximum, and then it started to go down. So we have seen this maximum, and thereby the smoke, so to speak, of the compressibility. So that was one of the thermodynamic response functions I talked earlier on. That's an indication that there can exist a critical point somewhere in the neighborhood. Could we see it also with the heat capacity? And this is, I show this now because this is was published just a few months ago in Proceeding of National Academy of Science. And this experiment was done at the Swiss lab. And we developed a way to measure what we call an ultra-fast calorimetry using the X-ray laser. And it's again using X-ray scattering. But so we have the droplets coming in, and then we are putting an infrared laser pulse, actually the same type of frequency as we did when we heated the Amorphous Isis. But now it's a very, very small pulse that will heat the sample up maybe only half a Kelvin. Very, very small temperature rise. And so we then come in with an X-ray laser pulse at a delay of roughly 1 microsecond later to look at that sample. We can do it then without heating and with heating and compare them. And from that, we use the X-ray pulse as a thermometer because we know the Q position here in the scattering. We have measured that very carefully as a function of temperature. So we can determine then how much we heated the droplet with the infrared pulse. And since the infrared pulse is constant between all the different hits or different also position of this droplet dispenser, so to speak, which corresponds to the temperature, we can thereby see how much we heated it depending on the temperature of the sample. And from that, we can of course determine the heat capacity. And as I said, this was done in Swissfeld. We were actually the one, I think, the first experiment in one of the hutches at Swissfeld. And then we could determine now the heat capacity as a function of temperature. And we again see actually a very rapid rise here of the heat capacity up to maximum. And then it comes down again. So we observe this maximum also in the heat capacity. And we can now plot a number of these properties as a function of temperature. Here is the heat capacity. There should be a little shift here actually. I always use an old figure because we needed to correct the temperature scale because in the calculation of the temperature of the droplet, the heat capacity comes in, and nobody had foreseen such a rapid rise, so high value of the heat capacity. Actually, almost all molecular dynamics simulation only gives a maximum around here. So the changes in the liquid is much more dramatic than these simulations. And I will come back to that later. We've seen a maximum at the isothermal compressibility is actually at the same temperature. I didn't talk about what's called the correlation length, which is more the length scale of these fluctuations that also have a maximum, which is, I will come back to that in the cartoon. It's a little bit like these blue regions. And if we plot that I showed you before, the derivative here of the structure factor with respect to temperature, which also has a maximum. So we've seen actually four of these maxima, which actually then is a nice confirmation of the existence of this Widom line, which I then say is the smoke from the critical point. We have not seen the critical point, we have seen the smoke. So this is an interesting picture, a little bit similar to what I showed before, but there is something added to it, which is this little bit grayish boundaries. Again, here are pressure, temperature. Here we have the two liquids, which would be then simple liquids, high density liquid, low density liquid. We have a critical point, one phase, and then we have these fluctuations. We call this like a funnel here. When you are inside this funnel, the liquid behaves anomalous with these fluctuations. When you are outside the funnel, it's more like a simple liquid, only one or the other. And the funnel becomes more narrow the closer you get to the critical point, and this Widom line is more centered inside this funnel. So if you get very far away from the critical point, of course, these regions that develop will become smaller and smaller. Everything will be more washed out in these fluctuations. So many of the theoretical simulations, when we look at them and we see where they have estimated the critical point, is typically roughly at the pressure of 2 kilobars. But our experiment looking at the Widom line, we can then estimate how sharp that rise is in the thermodynamic response function, and use also simulations to verify that, but just shift the simulation in pressure to get a good agreement with the experimental data. We have to shift simulation by 1 kilobar. So it looks like the real critical point is roughly around 1 kilobar, between 800 bar and 1 kilobar pressure at the temperature around 215 Kelvin. So it's not so far away from our conditions, actually. Whereas the simulations put this almost at 2 kilobar, and that's why the simulation are more washed out, and also the simulation doesn't give as dramatic increase in the thermodynamic response function as the experiment, and therefore also underestimate these fluctuations. It's a big challenge for the for real theoretical description. The interesting thing is also that our region of life is within this anomalous region, and that also means that all electrochemistry measurements are also in this anomalous region, where water are influenced by this presence of this critical point. So just go back a little bit and think about how is it that with ordinary water, so to speak. And in ordinary water, we don't have two liquid phases. As I indicated, we will instead have these fluctuations. And when the water is warm, it's more reddish, which was more yellow in the cartoon. And as you get more colder, you get more and more blue coming in, as you can see here, when it fluctuates. And why I bring in this is because we made a very nice cartoon here. Whereas in a simple liquid, we have only one form, and everything is just moving around with thermal fluctuations. But water then has the ability to then go from red to blue, so to speak. And that is also the reason for why water has high heat capacity, because, as you know, temperature is related to kinetic energy or particles, how fast things move, either in a vibration or translation motion of a molecule. But when you do a phase transition, you have to put in a lot of heat without changing the temperature, and it's because the heat goes to break and form bonds. And therefore, some of that heat that you put in or take out goes in water to change the blue from red or the red to blue, which doesn't give kinetic energy to the particle. And that's why water has a high heat capacity. Whereas when you're in a simple liquid, nothing of that happens. It's only going into giving kinetic energy to the particles in the simple liquid. So let's come now to the density maximum and see if we can understand why that appears in this picture. So this is now where we think we have roughly 100 degrees of boiling water, and we only have red molecules. and they are taking up quite a lot of space because they are moving fast and hitting it, colliding with each other, etc. As we lower the temperature, the volume decreases because they are moving less rapidly and they are taking up therefore less space, so to speak. And then if we eventually lower the temperature more, of course it contracts more, but just around 50 degrees, where we had that minimum in the compressibility, we start to have these blue molecules, which is the low density, and they take up a little bit more space. And as you thereby lower the temperature more, the volume in the glass doesn't sink any longer. And it reaches exactly a balance at 4 degrees, where the contraction of the red with decrease in temperature is balanced by the appearance of the blue that takes up more space. And if you now go into lower temperature to 0 degrees, we get more blue molecule and they take over, and the volume now increases. And then we can go into supercooling, and of course we get more and more blue and the glass increases. So we can here in a very simple picture understand why we actually have a density maximum in water. And actually the maximum change in density, which is not in the presentation now, but I can mention it, is actually at the Widom line. So if you would plot the density derivative as a function of temperature, they will have the highest slope at the Widom line. That's why the density will change most rapidly, so to speak. So let me summarize this up a little bit. I think I've been talking for a long time, but that's what I got the instructions here. That I have generated a scenario of understanding water, as you can see in this right picture, with the existence of a critical point that we haven't seen yet. We are attempting now to do an experiment to go there. But we have seen that we can go between a phase transition crossing here as we are in the no man's land here, changing pressure. And we have seen that when we come from cooling liquid droplets down, we can see that it's changing continuously. We have a one phase region. And if we go from two phases to one phase, we need to have a critical point. But also that we can see this smoke here in terms of the maxima in the thermodynamic response function of compressibility, heat capacity, but also correlation lengths, which I didn't talk about. So with that, I like to acknowledge a lot of people. These are the team that have been doing the experiment at PAL. I can also mention that this small angle electric scattering with the compressibility measurement was also done at PAL with a similar team. We are inside here one of the X-ray hutch, so to speak, and I can comment, maybe some of you might have heard the name Katrin Amann-Winkel. She made her PhD in Austria, in Innsbruck. And she's actually, yes. And then also I should mention, let's see, Fivos Perakis, that is at Stockholm University, is now a new assistant professor, and King Wan, who is actually was a postdoc, but now he is a professor in Korea, and then a big team. And we have another team here around this Swiss Fell experiment, a lot of similar people, few people from KTH, but also again King Wan from Korea, and then beamline scientists here also from at Swissfeld that did the experiment. So a little bit of a teaser. I put up this at the end here. Questions to think about for electrochemistry audience. Is the water only a blue background in electrochemistry? And we know that there is an electrical double layer. We know that there needs to be protons going in and out to an interface between the bulk during electrocatalysis, for instance, whether we do water split in fuel cells or CO2 reduction. Will this be important? We know for some experiment we did, I didn't talk about it, but we actually made a water films on barium fluoride, and we measured with X-ray absorption spectroscopy. And we compare, with a few layers of water, and we had the water at the liquid state, not frozen into ice. Very challenging experiment. And we compare this then to model spectra, and we came to the conclusion that the liquid that was just a few layers in contact with the barium fluoride was high density light, actually. And this was also in a simulation done here, where you can see going out from the surface into the bulk here. In the simulation, you see more a traditional liquid-like behavior here from the simulation that maybe overestimate a little bit these tetrahedral structures. But you had a very big difference here with what is to call the contact layer here at the interface. And that formed a high density liquid-like structure that was a little bit disconnected from the rest of the liquid. And here's a molecular dynamics simulation that was done by David Limmer and David Chandler in Berkeley. Of course, these are classical potentials because you needed to simulate this on rather large length scale and time scale, so you can't use ab initio methods, but was on a platinum 1-1 surface. And they also saw this compressed first layer here of water, as we saw here in the barium fluoride. And then outside here in the liquid, they saw what's called wave nature, where there will be big fluctuations, and sometimes these will come in and make contact with this first contact layer. And this happened over rather nanosecond timescales here. So question is, of course, are we only having a blue background here? How is an interface affecting these high density, low density fluctuations? We know that ions affects it as well. And of course, at an electrochemical interface, you have also the electrical double layer that will also influence it. So we have a mixture of both ions present there at different concentration, probably also changing its positions with depending on potentials. And then we have this interface itself, which can also have different adsorbed species and also, of course, adsorb ions as well, that can affect these fluctuation between high and low density. And of course, we have to come in and out of reactants. And can that also play a big role for be affected by these fluctuations? So, and particular proton transfer. And that is, of course, in my view, an open question, but we don't know much about actually. And I think from an experimental point of view, it's extremely difficult to study, but it's something, a challenge for the future, in my opinion. Just pointing that a little bit to your field. We have a similar discussion also related to biology and life processes, where there is a lot of still mystery inside the cell, where water could be a communicator for different aspects, which is completely not understood. So maybe water is not only a blue background, there is something more to it that we are yet to be discovered. So with that, I thank you very much for your attention for this very long talk, and any questions, please.
Thank you so much, Anders. Any questions so far? I think the audience can, 1 second. Yeah, the audience can ask questions directly now. Or maybe I can start so far. So you mentioned about the two liquids here. So I'm curious, is there any maybe indications from these simulations, although I doubt that it can provide enough evidence, or maybe from spectroscopy, which would be a better option in this case. How far, or what is the difference in the proton transfer rates in the two density liquids?
Nobody has studied it.
Big difference, or
no? Nobody has studied that.
Okay.
Unknown. It's a good question. I mean, that is. I can tell you that the simulations, actually, this liquid-liquid transition was first was an hypothesis coming from simulation in 1992. And there are papers now with more accurate simulation. They see this liquid-liquid transitions. But it's extremely hard to simulate because the temperature is rather low and the simulation becomes very sluggish. So they are so it's, I would say, in the beginning, but it's a good question, and I could imagine that it can be very, very different in the two different liquid forms. For instance, diffusivity, how fast the water molecules diffuse. If you're on the high density liquid side at the same temperature, just in pressure to be in the high density compared to the low density, the diffusivity is a factor of 100 faster in the high density. And that might tell you a little bit that the molecules are much more immobile in the low density, and we could imagine that the proton transfer rate will scale a little bit with the mobility of the water molecule. For the water molecule also to rearrange
Yeah.
in time some sort of proton transfer mechanism.
And a question from the chat. So how homogeneous is the pump pulse heating laterally? And maybe I can also add a question. How do you know that that pump pulse, the IR pump pulse, really hits to a specific temperature? So is there any way to calibrate it? And
Yeah, I skipped over that. So we have, first we demonstrated that we actually could melt hexagonal ice. So we know that we can heat it substantially. And then we looked at, after we heated the liquid into the high, as I showed you, eventually it crystallizes. And then it crystallizes then at a specific temperature that the sample has. It hasn't yet cooled down on these time scales. And so we looked at the position of the Bragg peak, which of course is depending on the temperature, and we can thereby sort of estimate what was the temperature after the IR pulse.
and maybe you can give a quick comment also on how the samples were prepared for these measurements at Paul.
So we you saw the sample holder with the small holes in it. And maybe I go back. Let's see if I can do that quickly enough. If I go back to that picture here somewhere. Any slides? Yeah, here we see the sample holder. So this ring here, the bigger ring, which then fits into the cryostat here, that ring is put in our pressure machine, and then you have two different pistons, and we have a specific indium layers here in between as well, and then we fill that with water, cool it down, it freezes, and then we put pressure and it quenches into this high density amorphous ice inside these holes. But there was a lot of development because we wanted the thickness here only to be between 50 and 100 micron, so it matches well with the penetration depth of the infrared laser. So if it would be too thick, the sample would be too inhomogeneous heated. So you prepare it then inside what we call a press with two pistons, crushing this together, and then under pressure you raise the temperature, and you raise the temperature a little bit to put it in the under pressure into this ultra viscous state. That means that the amorphous ice crushed ice sample, amorphous ice sample, goes a little bit into this ultra viscous liquid, and then you cool it down. So we come a little bit from the liquid phase into the solid phase again, and that means that we're actually generating more glass actually, because the glass is when you come from a liquid that you cool down without crystallizing, and that made the sample more homogeneous. But this was a lot of development to establish this protocol. Then we cool, after we have generated that, we cool everything down to 80 Kelvin, and then we take it out from the press, always inside liquid nitrogen, and we we never take the sample out of liquid nitrogen. We transfer it to Korea in special duver that we can actually ship on the plane. Comes to Korea and liquid nitrogen, and there is a special technique with certain gloves and so on to mount samples inside liquid nitrogen all the time. and then putting it into cryostat. The only time we are not in the liquid nitrogen is when we are uh, when we are moving the sample rod, the cryostat, into the vacuum chamber before the liquid nitrogen flow comes on, so to speak. So it's quite an elaborate technique to generate the sample. Then how laterally homogeneous is heated, we have, if I remember correctly, we have roughly 5 times bigger focus of the infrared pulse than we have of the X-ray pulse. So even though the heating of the infrared pulse is of course a Gaussian, so to speak, but where we probe the sample, since we have a much smaller focus of the X-ray pulse, we probe it where that is rather flat, so to speak. So we are laterally quite homogeneous, so to speak. The more challenge is along the sample, because the infrared pulse is of course heating a little bit the front side more than the back side. Yeah.
So that's a pretty impressive experiment. And so one question that comes from the YouTube, and I just remind that everyone can ask there too. It's related to the confinement. I guess you already spoke a little bit about the solid-liquid interfaces and how this work can be related to it. But the question is, if you have liquid confinement, you have water confinement, and that's something that we see all the time in many experiments that we do. How would this sort of due to liquid condition that is present in liquid water, how is it manifested then? Is there any way to extrapolate these results into the confined interfaces, confined spaces, and so on? Or if,
Yeah, I think this is still an open question. I can say that there were attempts. This experiment is about how to beat no man's land and do this experiment with ices form very rapidly. Was another approach where people said we will generate liquid water inside small pores, and they are so small that water cannot freeze. And people did a lot of experiment there, made claims that they see certain things, but that was very much rejected by the community, because that if the pores are so small that they can't freeze, it will also affect these fluctuations. Um, and indeed, eventually also simulations show that if the pores are too small, you will affect the fluctuations, between these regions of high and low density. What the size of the pores will be when it's affecting it, I think that's a future research question. Um, but I think as interfaces and pores probably will make water to be more high density liquid. This would be my guess, because you have a hard wall and it's more difficult to fluctuate. And each time you fluctuate to make a low density, you need to increase the volume. And that might be difficult when you have a rigid wall, so to speak, in the fluctuations then. But this is only a guess from my side. What pore size that this will be, and depending on the material in the pore as well. Um, these are excellent future research directions.
okay. Anyone can ask or interested in asking direct questions, because so far I'm reading from the chat. It's probably not the best way to ask questions. Okay, now maybe I will also ask one question that was quite interesting to me from the very beginning, that is related to the isotope effect. So how big is it? Because in electrochemistry, we don't see a significant isotope effect. But so there might be some way to sort of approximate the effect of this high pressure, low pressure liquid states to the electrochemical experiments through the isotope effect. Because if it's quite well manifested in the regions of stability of these liquids, but it's not manifested in electrochemistry, maybe it's not really important for electrochemistry.
Yeah, I mean, let's see. Do I have a picture of that? You can see it, for instance, here. We have also studied the D2O, and you can see as the cooling curve here. how D2O comes down. It's in general a rule of thumb, and we have a paper where we also have shown this, that the structure between H2O and D2O, it's almost like D2O is H2O that is 5 degrees colder. So it's like a temperature change of 5 degrees. So many of the properties between the two isotopes is you can relate the two isotopes by just shifting the temperature by 5 degrees. That's not a very big effect.
Okay.
However, the critical point, I think, is more where it's exactly located in pressure. That might be a bigger effect, but we don't know that yet. We have some indication that that might be the case. Um, yeah.
All right. There is a question from Yang Shohur.
Hi, Anders. Thank you so much for the amazing talk. So just have a basic question. Perhaps I missed it from the beginning of your presentation. Could you elaborate and explain why we have two different densities of water thermodynamically?
Why the two different liquids would have different density?
Right. So thermodynamically speaking, why would we form these two different water with different densities, right? Is that due to change in, let's say, the hydrogen bonding, or it's this entropic effect? And
yeah, so of course, thermodynamically, if we have these two liquids and they're in equilibrium at this low temperature and at a certain pressure, it means, of course, that the free energy of them are the same, right? So usually we can think about that the low density liquid can make better bonds. So it's probably having a better bond energy, more efficient in hydrogen bonding, and therefore will have a lower energy. Whereas the high density is more entropic. And since both of these contribute to the free energy, you thereby can have a situation where the free energy of them are the same. Um, and this is probably one of the biggest challenges with water, also from a theoretical point to describe this, is that in order to have these fluctuations and all of that to come out to be correct, you need to be able to describe not only the bond energy, but all the entropic and all the, all the contribution to the entropy very accurately. And particularly the contribution to the entropy has been shown to be very difficult to describe. So if I make a little bit of a simple analogy here, or simple description, you can think about that the low density liquid is almost locally looking like ice. It makes four bonds, so to speak. And and by making four bonds, like in ice, it can then optimize the hydrogen bonding strengths. So you get rather good, strong hydrogen bond. That's why, of course, we form ice when we go down to low temperature as the stable state, so to speak. The high density is high density because we can move in water molecules that are not, I didn't speak so much about this, but we can move in water molecules which we often call interstitials. They're a little bit in between, and that means that they are more interacting with the other water molecules with van der Waals forces, more van der Waals forces. And if you have a van der Waals forces, you have a more an isotropic interaction. If you think about the hydrogen bond, which is more directional interaction in the tetrahedral structure. And these more van der Waals type of forces, of course, allows much more degrees of freedom for arrangement of water molecules. And therefore you get more entropy. Did this help you?
Yes, thank you so much. And this is excellent. Thank you.
Further questions? I think Yelena certainly has some questions too.
Yes, thank you, Anders, for this interesting talk. I want to tell you a special strange story about water at the interface. There are several experiments going from quartz crystal microbalance admittance from other observations concerning a sort of frozen of water near the interface in a relatively thick layer up to micron. And people never trusted these experiments. But there are at least 3 of them which were done by reliable people. What do you think? Can this phenomena take place in 1 micron layer at room temperature?
I know also that there are experiments by someone called Jerry Pollack in Seattle, and it's been very controversial. He called it the fourth phase of water, which I don't think is a new phase, but um, there are evidence. Actually, I can just tell you that we have just finished. You saw some of the clips in my presentation, which is from a water movie. So we have been putting together a TV program about water. We will see how it will broadcast. But we will see in that program that we actually are having, we are interviewing Sylvie Roque in Switzerland. She is in Lausanne. And she's done a very interesting experiment where she can look at with non-linear optical methods on see correlations between water molecule in this angular correlation, where two OH groups, so to speak, are pointing along the hydrogen bond, so to speak. And if these have a correlation, she gets what we call a second harmonic signal. It's not some frequency that people often use, but it's more a second harmonic signal. And she has studied that how that second harmonic signal depends on when you put ions in water. And then she came very surprising results. It's been very controversial that when she put simple ions in, she saw this effect coming at very, very dilutions. And she derived it to that there are 55 million water molecules affected by a single ion. Now she did it further with polyelectrolyte, which might be a little bit more relevant if you have an interface, because this is of course a very large molecule that is charged, and the same measurement then was even more extreme. And there she saw that one polyelectrolyte molecule affected 55 billion water molecules. How we translate that to what I now say in this presentation is, of course, speculations, and we don't know. But I have had similar discussion with biologists that if you have this fluctuation now between low and high density liquid, and even at ambient temperature, and the low density liquid might be clumps of the order of 30 molecules at room temperature, something like that. And they are popping up on the picosecond level, we think, at room temperature. As you cool it down, they are staying longer, but they have very short residence time. So they fluctuate. Almost you can think about fricadelle in a soup. We are popping up a fricadelle in a soup and it disappear again. So from a first point of view, you will think that all this fluctuation is completely random. But it's not like a computer network where you will think about the 0 and 1, because that are more static structures. But this is dynamically changing all the time. So we can envision that is it completely chaotic if you have a disturbance somewhere as an interface, or you can have a biomolecule, a biological membrane, and so on. Are these fluctuations no longer random, chaotic? Or is there a correlation how these fluctuations are on long length scale and long time scales? And these are, of course, fascinating topics for the future, because it can bring in many aspects of water, close, interfaces where it could affect on micron level, micrometer level, as you pointed out, but also in biological cell with communication between different components in the cell. So far that we have very little tools to investigate this. But at least we are now knowing that these fluctuations exist, but can they be correlated? And that maybe go into your question that you asked.
Oh, thank you. Can you tell again the name of this second harmonic generation lady?
Sylvie Roque in Lausanne,
Mm-hmm.
EPFL,
Mm-hmm.
ROKE, Roque.
Mm-hmm. Thank you.
And she's looking also at biological membranes and so on. So, yeah. But wait to watch the water movie when it comes. I don't know where it will be broadcasted, but it's a 90 minutes film with many of these things that you also heard here about.
Many thanks.
More questions? I see that another hand is raised. In principle, you can just ask. You don't have to raise your hand as long as the microphone is free.
Hello, Anders. Nice to see you again. I hope you are well.
I don't know who is speaking now. Let's see if I go out to stop sharing. So I recognize a few voices here. Who are you?
Song.
Okay, good.
I just a question. Do you think we will ever understand water?
I mean, I think you can put that to any topic. You can always go deeper and deeper in the topic. I think I think we only have scratched the surface of water. If there would be this what I call dynamic correlation on long length scale in the liquid, that can have an enormous implication on many different things, going into health and life processes and everything. So I think there could be decades of research before we understand any of that. But we don't know if that is actually happening or not. So yes, we are making progress. I can tell you these experiments that we show now with the liquid-liquid transition and so on, if you talk with the theoretician who proposed this, they thought it would never be possible to measure. But now we made a big step that we can actually measure it. And maybe someone else can take other big steps in the future with new type of experiments. Maybe yourself that could bring more knowledge into this field.
Maybe, but thank you very much. Nice to see you again.
Good. They're nice to see you too.
Hello, Anders. So I'm curious about this in the funnel region. You know, you show that you had these fluctuations between LD-like states and HD-like states. Do they have some characteristic time scale, and do you interpret that as a barrier?
Yeah, I mean, if there is a barrier in these fluctuations, I'm not sure if I would interpret it in that term, because it is sort of a little bit a barrier that is coming now, is sort of originating from this critical point. The time scale has not been directly measured, but I can only infer from different type of experiment that I think the time scale is at room temperature of the order of 1 or 2 picoseconds. They would exist, and then they sort of fluctuate out. If you go lower the temperature, the time scale increases, and it's often related to what people talk about the relaxation time in water. We have been attempting to do some experiments, but not yet successful with the X-ray laser, where we can look at what's called X-ray correlation spectroscopy to get to this time scale. But would be my guess. You can think about it a little bit like this, that when water is very hot, let's say just between 50 degrees and boiling, we have almost only high density liquid. There might be forming a single molecule that is tetrahedral coordinated, dissolved in the high density liquid, but it will still be in more high density liquid forms. Now at a certain temperature, where the dynamic in the liquid is slowing down and the molecule is moving a little bit less rapid, these tetrahedral molecules might then start to form, and they they can clump together. So a tetrahedral can bond to another tetrahedral, and then they start to form a region. When water is still hot, they can only stay together during a very short time, and therefore they cannot become many, and they cannot become in a larger region. As you cool the liquid further down, and you can generate more the tetrahedral water molecule, because, as I said, it's less entropic, so it's not so favored by having temperature. So as you generate more of these tetrahedral molecule, and they can then bond together longer, because the residence time will suddenly become longer, and they can become bigger regions, so to speak. And this will continue as you lower the temperature towards the Widom line. As you go beyond the Widom line, then everything will become only low density, but nobody has really been there yet, because ice will be formed so rapidly. So, but this is only guesses for me. I would probably expect that residence time of these 1 to 2 picosecond at room temperature. At the Widom line, it might be 100 picosecond. Is a guess.
Okay, thanks.
Anders, maybe I can also ask a question if no one else has any other questions, because I don't see anyone unmuting themselves. So somewhat recently, there was a paper published by the group of Willem Goddard from Caltech that some people found a bit controversial. It's a theoretical paper, but I'm curious what maybe you saw certain features that they predicted. So they predicted that upon melting from ice, water bonding goes from a fourfold to 2 plus 2-fold. So 2 weak bonds to strong bonds for each water molecule. So as a result, water looks like some sort of a branched polymer.
Yes, I know that study.
Right. So is there any are there any indications that you observe in your experiments that could prove or disprove this theoretical work?
So let me put this study. I mean, I think they are onto some aspect of it. I think they're onto, but that paper contains so many errors. Unbelievable statement of X-ray scattering, all sort of things that are errors. So it's a little bit sad that it contains so many errors. Therefore, it's completely rejected by the water community. But at the same time, this idea that there could be these two hydrogen bond structure is actually a little bit along the ideas that we proposed in 2005. We published a paper in Science based on spectroscopy then, that water at room temperature will be mostly hydrogen bonded. So let me put that statement a little bit of the context of this talk. So the high density liquid, as I talked about, will have these interstitial molecules coming in at roughly 3.5 angstrom, but still be a lot of coordinated around the water molecule, a little bit bent hydrogen bonds. But that, of course, high density liquid exists under pressure. And if you remember, maybe I can go here in my talk. Let's see where I have a phase diagram, maybe here. So that would be the situation when we are here, so to speak. You have pressure, and that will keep the molecule bonded together very much around the center molecule, but you will have this additional interstitial filling out the room that you will typically have in hexagonal ice. And that makes it to have a higher density. But of course, as you move now and lower the pressure, we go into ambient conditions, and then we have this fluctuating with the yellow and the blue. The yellow now are still high density with these interstitials, but we have not any longer the pressure, and therefore, and I'm just actually in the process of putting this together in a big review paper, but I have some evidence that the water in this high density has changed a little bit the structure in the first coordination shell. And actually it will be more two hydrogen bonded structure, similar to what we proposed in the 2004 science paper. And they could thereby form long chains as that Caltech study. But water will never be entirely that, because you will also have the blue region, which they didn't see in their simulations, right? So they might have been onto something related to the blue here at ambient pressure, because the yellow here in this region locally will have a much lower density than it has here when you have pressure on it. So I think they're onto something, but they were doing a lot of other things in that paper that unfortunately got it a little bit, lost a little bit its value, if I put it like that. So yeah. Did that help to answer the question?
Yes, absolutely. Yeah, I think I got some idea about it. I see another person raising their hand.
Yes, hello, can you hear me?
Yeah, I can hear you.
Yes, hello, Anders. Thank you very much for the nice presentation. I have two short questions. The one is, so essentially, now from continuation from Andrew's question, so do you think then that the high density liquid and the low density liquid have also many differences in the average number of hydrogen bonds formed per molecule?
Yes, they have. But it depends a little bit also on pressure, as I said. So in what I've recently analyzed in a certain way, X-ray scattering data, that that when you go to that what we think is the high density region here, when you have but also it comes in how you define the hydrogen bonds. So if I would define the hydrogen bonds as number of water molecules that are, let's say, within 3 angstrom from another oxygen atom, where you have more real hydrogen bonds, so to speak. The low density liquid will have 4, always similar to what you have in tetrahedral ice. Under pressure here, you will also have 4 plus the interstitials, which will then create a high density. But the yellow here will more be towards 2. Because there will be a few of them that will expand a little bit out. But that will also depend on the temperature, because if you also have the yellow here, at room temperature, they might be a little bit close to 2, but when you cool it down, they will come closer again to each other. And of course, then it's a grayscale, what you mean with the hydrogen bond. So they will come closer and closer together. And probably at low temperature, the yellow here will not be so different as it is under pressure. So to speak.
Okay, thank you. And if I may ask one more small question. The animation that you showed with the vertical tube, where we'll start to see the LDL starts forming at 50 Celsius.
You mean the glass, the water glass with the balls in it?
Yes, yes.
The density maximum.
Yeah, yes. This one at the 50 Celsius, the 50 degrees Celsius. I remember you said that there you notice that the LDL starts forming where the blue balls start to appear. Is this estimation from experiment or from computational studies?
Experiment. And the reason why I know that is that you can have blue single molecules coming in the HDL, but when they start to form clumps, it's in that around that temperature. And it's also data that I didn't show, but we know that from X-ray scattering that there is a particular correlation at rather long bond lengths. Let me go back here. If I go in the right direction here. At rather long bond lengths, where we can see the central molecule in one of these clumps, and we can identify that it is more in this low density liquid situation. That correlation has 0 contribution until you reach the temperature of 50 degrees, and then rapidly it comes up. And when that comes up, let me go back because I want to find the compressibility again. Here. And it started to come up exactly at this point here where the compressibility has a minimum, just before here. So it means, of course, that the reason why the compressibility changes sign is because you start to get fluctuations now of region in the liquid that has a bigger volume. And that will, of course, increase the volume fluctuations. And that's why it changes sign here. So that is this is the boundary for when it happens, which is very sensitive in the compressibility.
Well, that's very interesting. Thank you.
And it matches exactly when we see that correlation at 11 angstrom between water molecules that we can assign to these LDL local structures. So it means that we have a center molecule and we have an LDL structure that can go out all the way out to 11 angstrom with only LDL molecules. And they don't exist here. They only appear just here, exactly at the point when the compressibility changes sign.
So after that point, basically, almost the whole water structure is just like the HDL.
Yeah, I mean, I would say that in this region, it's mostly HDL, but there might be a single water molecule that is an LDL, right? Tetrahedral, but it's more like a defect or a little structure that is formed inside the HDL network. I will call more LDL is when it's formed a region with a clump or number of molecules, and that's not up here.
Okay.
Pure water.
Thank you very much.
All right, thank you so much, Anders. I think that at this point we will wrap it up because we have plenty of questions and a very thorough discussion. So I hope everyone enjoyed it. Thank you again. And then we hope to see you, all of you, again at the next colloquium in 2 weeks.
Thank you very much for listening. My pleasure.
Thank you.